Hello everyone. I'm Shaima Sadeq, a fifth year student now, and I'm going to be talking about bioenergetics today. Feel free to stop me at any time if you need further clarification. And I'm going to try to keep it as brief as possible because I know all of us have to study. Okay. All right, so let's start with an introduction. Thermodynamics is a branch of physics that deals with energy changes, and bioenergetics is a part of thermodynamics. So it talks about energy changes during metabolic reactions. Now, for the two fundamental laws of thermodynamics, the first one is that energy is conserved. So you cannot create or destroy energy. It can only be transformed. So it can change form or it can be transferred from one place to another place. And the second one is that with any spontaneous chemical or physical change in the universe, the disorder of the universe increases. So this means the disorder is also called entropy, and this is something we're going to further talk about a bit later. So the entropy of the universe increases in all these natural processes. Now, this is again looking back to the previous slide. So with any living organism, they cannot create or destroy energy. They can only transform it. And while transforming energy, they're going to increase the entropy of the universe. Now we'll talk about something called free energy change or Gibbs free energy. This is the energy that a living cell can use to do work. And it's a measure of the chemical energy available from a reaction. The way to calculate Gibbs free energy, which is denoted by delta G, is the free energy of the product minus the free energy of the reactants. Now, the relationship between Gibbs free energy and some other entities are going to be talked about now. So let's look at this equation first, the Gibbs-Helmholtz equation. Delta G is equal to delta H minus T delta S. Delta H is enthalpy. So a change in enthalpy talks about whether heat is going to be released or absorbed during this reaction. And T is temperature, which is going to be in Kelvin for this equation. Delta S is change in entropy. Entropy, like we mentioned before, is disorderliness or randomness of something. A simple way to put it is to compare solids to liquids. Solids, the molecules in the solid are more stable. They're just sitting there, whereas in a liquid, they're moving around. So a liquid has more entropy, more disorderliness than a solid. And both delta H and delta S by itself does not predict whether your reaction is going to be favorable. What predicts that is the delta G, which is the change in free energy. And delta G is going to be 0 when your reaction is in equilibrium. Okay, so enthalpy again, the H, it represents the heat content. So if a reaction releases heat, it's called exothermic, and delta H is negative. If a reaction absorbs heat from the surrounding, it's endothermic, and delta H is positive. Entropy, like we said, is the disorderliness or randomness. And all reactions are going to increase the total entropy of the universe. So like everything's going to become more disordered. And even though okay, so we have something called the system, which is the reaction itself, and the universe is like everything around it. So the entropy of the system could increase or decrease, but the overall entropy of the universe has to increase. That's the second fundamental law of thermodynamics, like we said before. Now, exergonic and endergonic reactions. These words refer back to delta G. So if delta G is negative, It means the reactions are going to release free energy. And this reaction is spontaneous, so it can happen easily by itself. That's an exergonic reaction. Endergonic is if the reaction has to absorb energy from the surrounding, and the reaction is non-spontaneous, so it cannot happen on its own. It needs a little push for the reaction to go ahead. And that's endergonic, and delta G will be positive in this case. So it's important to note that exergonic and endergonic are not the same as exothermic and endothermic, because exothermic and endothermic refer to delta H, whether delta H is positive or negative. Exergonic and endergonic refer to delta G. Okay, now we have an example here. So we mentioned this equation before. Delta G is equal to delta H, the change in enthalpy, minus temperature, into delta S, the change in entropy. And so the delta G depends on both the change in enthalpy and the change in entropy. Yes, exothermic and endothermic is for heat, which is enthalpy. Okay. So this is the reaction we're going to look at. Water solid, which is ice, going into liquid water, which is water, right? So the forward reaction is called melting, ice melting to become water. And the backward reaction is freezing, which is liquid water becoming solid ice. Now we're going to take three scenarios. And in scenario number 1, the temperature is positive 10 degrees. So we see that the delta H is plus 6.4, meaning this is an endothermic reaction. It's taking in heat. And then this is the T delta S. And then the delta G, after we calculate it, becomes minus 0.2. So can anyone say if this is endergonic or exogonic reaction? Yep. So that means that this reaction is spontaneous. So it is going to happen easily. So ice is going to melt and become water at positive 10 degrees. So the forward reaction happens. Now at 0 degrees, it's again endothermic. So it's positive delta H, meaning heat is going to be taken in. And then this is the value for entropy into temperature. And delta G is 0. 0 delta G, 0 delta G is equilibrium, exactly. Equilibrium means the forward reaction is happening at the same rate as the backward reaction. Okay, so the rate at which the ice is melting is the same rate at which water is freezing. So looking at it from a broad perspective, you don't see any change happening. That's what equilibrium is. Right? And then at negative 10, again, delta H is positive. So we're taking in heat. T delta S is this. And then delta G becomes positive 0.2. Can you guys say if it's endo or exo now? Yep, so it's endo, which means like this reaction is non-favorable, the forward reaction, right? So at minus 10, melting is not favored. It's not spontaneous. Rather than that, the backward reaction is going to happen. Freezing is going to happen. And it makes sense, right? Because it's minus 10 degrees, so water is going to freeze. Because delta G is positive, meaning the forward reaction is not favored, non-spontaneous, so the backward reaction happens. Slide 7. Okay. Did everyone get this part, or do you need me to repeat anything? Okay. Okay. I'll just go back to slide 7 then. The end. All right. So at minus 10 degrees, we see that delta H is again positive, meaning it's an endothermic reaction. We're taking in heat from the surrounding. And then this is the value of T delta S plus 5.4. When we calculate it using this equation, I get a delta G of plus 0.2, right? Like I mentioned before, positive delta G means the reaction is non-spontaneous. Non-spontaneous means it's not favorable for this reaction to happen, which is the forward reaction. So instead of the forward reaction happening, what's going to happen is the backward reaction. So the water is going to freeze to become solid because delta G is positive. Does that make sense? All right, so let's go to slide 7. Okay. All right, I'll just explain the whole equation again. So we see this equation, delta G is equal to delta H minus T delta S. And we're going to dissect everything. Delta H is delta means change. And now we're going to talk about the things. H is enthalpy. So it's with H, like we're talking about heat. Is heat going to be released or absorbed from the surrounding? And that's called exothermic or endothermic reactions. What's the difference between enthalpy and entropy? Okay, enthalpy talks about heat. So there are certain reactions, for example, I don't know, for example, burning something makes your surroundings hot, right? So that's exothermic, and it's talking about heat. So that's enthalpy. Whereas entropy is about disorderliness or randomness. We look at it from a molecular level, not from an outside perspective. So, for example, like I mentioned before, disorderliness is that, like how random something is. So if I take a solid and a gas, you know that the molecules in a solid are all like very packed together. They're not moving much, they're just vibrating. So that's low entropy, low randomliness. Whereas in a gas, the molecules are going crazy. They're just moving about randomly at very high speed. That's high entropy. They're like very disordered. I hope that makes sense. Endergonic means backward in reaction. Exergonic means forward. It kind of makes sense, yes. Wait, let's go back to the Gibbs energy part. Okay. It makes sense because, like, first of all, yeah, when we're talking about all these values, we're actually considering the forward reaction, right? So yes, so if it's exergonic, the forward reaction is spontaneous. So then yes, it would mean forward. And endergonic means the forward reaction is not spontaneous. So yes, we do prefer the backward reaction. Yep. All right, now this again, like this is a better visualization of entropy. Reaction is favorable. Okay, so let's go back to, okay, let's go back to here. With the double arrow, I can see that it's a reversible reaction, right? Ice can become water and water can become ice. But then the rate at which the reaction, one of the reaction is happening, determines what's happening on a bigger level. Is my ice melting or is my water freezing, right? Like we're gonna look at the bigger picture now. Can everyone else hear? All right. So for looking at the bigger picture, That's what I mean by the reaction is favorable, right? Because even since this is a reversible reaction, even when my ice is melting, a tiny bit of the water is freezing at the same time, okay? But the rate of the melting is so much higher that the freezing is insignificant on a bigger scale. So I'll just be like, okay, my ice is melting. That's what I mean by the forward reaction is favorable. However, if this reaction was at equilibrium, so the forward and the backward reaction are happening at the same rate, I see no visible change. The amount of ice and water that I have at equilibrium, it's going to stay the same because the melting and freezing are happening at the same rate. So they're compensating for each other. Whereas if my backward reaction, freezing, was favorable, I will see my water turning into ice on a bigger picture. Even though a tiny bit of the ice is actually still melting because it's a reversible reaction at the end of the day. But more of it is freezing. It's freezing at a faster rate. So I see my water turning into ice. Um, can you say what the last part you heard was? Okay, I'll just okay, I'll repeat about the favorable thing again. So I'm saying that by the double arrows, I can see that this is a reversible reaction, which means my ice is melting, and at the same time, my water is freezing to become ice. What I mean by favorable is which reaction is happening at a faster rate. Okay, so if more of my ice is melting, from a bigger picture, I'll see that the ice is melting. So that's the forward reaction is favorable. And if the backward reaction is favorable, I'll see that my water is freezing to become ice. Even though at the same time, a tiny bit of the water of the ice is melting, but that's a tiny bit because my backward reaction is favored. So I'll, from the bigger picture, I'll see that the water is freezing to become ice. Okay, now this is a good illustration of entropy. So we have two examples. First one, hydrogen and oxygen mixing to become water. We know that hydrogen and oxygen are gases, so they have very high entropy. And then when they're going to mix, it's an exothermic reaction. So the reaction gives out heat. I can see that my delta H is negative exothermic. And then they give me water. Water is liquid, so it has less disorderliness or less randomness of the molecules than my gases that I started with. That's why my entropy is positive, because I decreased the disorderliness of my system. That's why it's positive. And then the overall delta G is negative after calculation, meaning that this reaction is favorable. So it's favorable for hydrogen and oxygen to combine and form water. Here, I have sodium chloride, which is salt, the normal table salt, dissolving in water. So the solid structure of the crystals of salt is very ordered, like it's so tightly packed together. So very ordered means less entropy, because entropy is a measure of disorderliness. And then it's going to dissolve in my water, and then the molecules just move around, which means high disorderliness. So the entropy here is actually increasing, and we see that it's negative. It becomes more disordered. And this reaction takes in heat. It's endothermic. So it absorbs heat. Thus, my delta H is positive. And then overall, my delta G is again negative, meaning this reaction is also favorable. So one thing we can see from both of these is it's not, you cannot just, like, I think I mentioned this near the beginning when we were doing the equation, the delta G equals to delta H minus T delta S, that just by looking at delta H or delta S, you cannot say if a reaction is favorable or not. You need to look at the delta G, because here I had an exothermic reaction and my entropy decreased, but then delta G was negative, so my reaction happened. While here, it was the opposite case. My reaction was endothermic, but my entropy increased. And again, delta G was negative, so the reaction happened. So in both cases, I have a negative delta G, exergonic reactions, which means my reaction does happen. It's spontaneous. It happens on its own. All right, so free energy is a measure of the system's instability. So like it's unstable and unstable, and then it wants to become more stable. And during a spontaneous change or a spontaneous reaction, the free energy is going to decrease and the stability of the system increases. Because the free energy decreases, that's why the delta G is negative, and negative delta G is good. It means my reaction is spontaneous. At equilibrium, you have maximum stability, and we mentioned before, delta G is 0. A process is spontaneous and can perform work when it's moving towards equilibrium. So like basically all reactions kind of happen and they try to achieve equilibrium. That's what it's saying. If more disorderliness, then entropy is more. Yes, because entropy is a measure of disorderliness. All right. Okay. In equilibrium, you have no change in concentration of the reactant and products, no net change over time. So basically what I said, right? The forward reaction and the backward reaction is happening at the same rate. So my ice is melting. At the same time, my water is freezing. So if I look at it from far, I have equal amounts of ice and water. Nothing's changing. Even though from like the reaction perspective, both reactions are happening just at the same rate. Standard free energy change, delta G 0. When you see the sign, it always means standard. So this is the same as the free energy, delta G, except we have added some specific conditions. You need to have standard temperature, which is room temperature, 25 degrees Celsius or 298 Kelvin, standard pressure, 1 atmosphere, and standard initial concentration of reactants and products of 1 mole. All right. So the equilibrium constant and standard free energy change. We have an example reaction here. A is the reactant. It's going to turn into B, which is the product. And then you have this equation. Delta G is equal to the standard delta G plus RT ln B by A. Whenever you see the square brackets in chemistry, it means concentration. So it's ln concentration of B divided by concentration of A. And ln is the natural logarithm or the log E. You can just find it on your calculator, just do log E. No need to memorize. Now at equilibrium, we have something called the equilibrium constant, K equilibrium. It's equal to concentration of B divided by concentration of A. So for this part here, I can just replace it with this equilibrium constant. And we also mentioned before that during equilibrium, the delta G of a reaction is 0. So if I put 0 here, I can rearrange this equation to say that the standard delta G of a reaction is equal to negative RT ln of the equilibrium constant. And, oh, by the way, R is another constant here. R is the ideal gas constant. I think it's going to be there in the exam, so no need to memorize. All right, so we're gonna talk about the relationship between the standard delta G and the equilibrium constant. And just to recap, equilibrium constant is equal to concentration of the products divided by concentration of reactant. And our reaction was A becoming B. Now, if my equilibrium constant is 1, meaning I have equal amount of product and reactant, so equal, so they become 1. And at equilibrium, I said my delta G standard will be 0 then. And like none of the reactions are favored, so the arrows are equal size. A is becoming B. At the same rate, B is turning into A. So I'm not going to see a change in concentration of my product. Then if my equilibrium constant is more than 1, meaning my concentration of the product is more than concentration of reactant. So when I divide, it becomes more than 1. And my standard delta G is less than 0, right? So it's an exergonic reaction, meaning the forward reaction is favored. More of A is becoming B than the backward reaction happening. So I can see that the forward reaction is happening. Now, if the equilibrium constant is less than 1, where my reactant amount is more than product, so when I do B divided by A, it becomes less than 1, and the delta G and the standard delta G is more than 0, so it's an endergonic reaction, my backward reaction is favored. So more of B is turning into A, right? That's why A is larger in amount, because B is becoming A. And forward reaction is happening less. Did everyone understand this? Because this is one of the most important parts in the lecture. Okay. All right, I'll move on. This is simple. What's the difference between delta G and delta G standard? Like I said, delta G was the free energy change, right? And standard is when I specified standard conditions, which was standard temperature, standard pressure, standard concentration of reactants and products. All right. Now, free energy. This is another important slide, and it's really simple. So delta G is equal to delta H minus T delta S. Delta H was change in enthalpy, which is the heat. Delta S is change in entropy, which is disorderliness. And if delta G is less than 0, it's an exergonic or spontaneous reaction. If delta G is more than 0, my reaction needs energy to happen. So it needs a little push, meaning it's not spontaneous. And if delta G is 0, my reaction is at equilibrium. All right, now the gas constant, which is 8.315, and then the standard temperature. I don't think it's necessary to memorize. All right, we'll take an example now. So this reaction, glucose 1-phosphate turning into glucose 6-phosphate. When I was doing the experiment, my initial concentration of the reactant, which is glucose 1-phosphate, was 20 millimoles, and I had no glucose 6-phosphate. And then I put the enzyme phosphoglucomutase. After equilibrium was reached, the concentration of glucose 1-phosphate is 1 millimole, and glucose 6-phosphate is 19 millimoles. What is the equilibrium constant? If you guys remember, we said that the equilibrium constant is concentration of product divided by concentration of reactant, which is simple, right? But then we have two concentrations of the reactants here, 20 and 1. What am I going to use? It's simple, because it's called equilibrium constant, meaning I'll obviously use the equilibrium concentration. So the concentration of reactant at equilibrium was 1. So this is the number I'll use. All right. So here we do concentration of product divided by reactant, and 19 by 1 is 19. Now, if I wanted to find the standard delta G, it's this equation, and I put in the constants, and then I do len of the equilibrium constant, which becomes minus 7.3. And the minus delta G, like I mentioned before, means it's exergonic. So the reaction is spontaneous. So the reaction is going to happen. Glucose 1-phosphate is going to become glucose 6-phosphate. Is that example clear for everyone? All right. We'll just skip this. These are just the delta G of different reactions. Okay, now this is telling you that you can add delta G, the standard delta G. So if I have a reaction of A becoming B and then B becomes C in a separate reaction, I can sum it up to make B like a median product, which like reacts again to form C. And I add up the reactions to overall say that A becomes C, and I can add the delta Gs. So here is an example. Also, like the way I can add this is because B is a product here, and then B gets used up to form C. So I can just cut out B out of the equation and just say A becomes C. So for this example, I have glucose and phosphate becoming glucose 6-phosphate in water, and then I have another equation here. This phosphate that I had in the beginning, here I have it again. So I can kind of say that it's unchanged. So I'm just going to cut it out. And then I have water formed as a product in my first reaction. And then this water is used up in my second reaction. So I can again cut it out. So after getting rid of the stuff that are redundant, I can add up the two equations to say that ATP and glucose is going to give me ADP and glucose 6-phosphate. And to find the standard delta G of the overall equation, I'll just add them. So 13.8 plus negative 30.5, and then I'll just find the answer. I hope that makes sense. All right, now coupled reactions. I have a catabolic reaction here. By the way, catabolic reactions are exothermic, so they give out heat, and then anabolic reactions are endothermic, so they take in heat. I have a catabolic reaction here, so it gave me heat. I can use this heat to power my second reaction, the anabolic reaction. So I have a reaction making energy. I'll use that energy to do my second reaction. That's what a coupled reaction is. This is the same thing here. Catabolic is spontaneous. Yes. All right. Okay. Yeah, so I have a reaction number 1, which has a positive delta G, so it's endergonic reaction. And then I have an exergonic reaction, which is delta G negative, so it's spontaneous. Now, these two reactions combining together, when I add them up, the whole total delta G that I get is negative, which means my coupled reaction is going to be spontaneous. So that's good, because this reaction on itself was not spontaneous. So it's hard for it to happen. When I couple it with an exergonic reaction, the coupled reaction becomes spontaneous. No, I think it should actually be the opposite. Wait, which generate ATP are spontaneous? I mean, yeah, it kind of, I don't know. We'll see about that later. I'm going to get back to that question. All right. This again, we're just talking about anabolic and catabolic reactions. And then here is the breakdown of ATP? Exothermic, not exergonic. That's what the doctor mentioned in class about catabolic reactions being exothermic, but I think exergonic makes sense because it's energy here, not heat. All right, so for the breakdown of ATP, let's look at the structure of ATP first. You have the adenosine, and then I have the 3 phosphates. 2 of the phosphates are joined by phosphoric anhydride linkages, and then my 3rd phosphate is joined to the adenosine by an ester bond. The OCH2 is an ester bond. Okay, so when I break down my, this first phosphate bond thingy, the phosphoric anhydride bond, to get ADP from ATP, I release energy. I get minus 30 delta G standard. And if I want to break down 2 of these bonds, so I make AMP from an ATP, I get minus 32. So I'm releasing a lot of energy. But what if I have an AMP? So just this much, and I want to break down this ester bond. I only get minus 14 energy, like the delta G is minus 14 only. So that's not a lot of energy because it takes a lot of effort to break down an ester bond. So it's more efficient for the body to break down only the 2 phosphoric anhydride linkages. That's why I can make ADP or AMP from ATP, but our body doesn't usually break down an AMP because it's not worth it. Okay, it's negative, so the reaction is spontaneous, but it doesn't release that much of an energy. So it's not that useful. All right. So an exergonic reaction is going to make ATP. So getting back to the question, yes, generating ATP is spontaneous because exergonic reaction. So the exergonic reaction makes ATP, and then I will hydrolyze this ATP to get energy. And this energy I'm going to use in my endergonic reactions. So that's kind of going back to the coupled reactions thing. These are just other molecules that can give us energy when broken down. I don't think it's that important unless the doctor mentions otherwise. This is similar. Other phosphoryl group transfers. So I can break down this to become ATP and this to become ATP. And then ATP can be broken to give glucose 6-phosphate. But making ATP from glucose 6-phosphate is not favorable because I can see that the arrow is shorter. Okay, now energetics of glycolysis. Oops. All right, so glycolysis has a lot of reactions, but 3 of them are actually the important ones, reactions 1, 3, and 10, because these reactions are very strongly exergonic. They're very spontaneous. They help my whole process of glycolysis go ahead, because if all of my reactions are reversible, then there's always the chance of the backward reaction happening instead of the forward reaction, right? But I want all my reactions to go forward because I want glycolysis to happen. So these are the 3 important steps. Because I can see that when these reactions happen, I have a very strongly negative delta G. So it's negative, meaning it's spontaneous, and it's a large number, meaning lots of energy is made. Yes, they're the committed steps. They make my reaction go ahead. They make sure that I'm not gonna. Isn't step 10 actually step 9? I think it's 10 if I count. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, it's 10. All right. So yeah, the two things I mentioned, it's negative, so it's spontaneous, and it's a large number, so a lot of energy is released, which is good. Because let's compare the other steps. Here, the difference between my reactant and products is barely anything. Even like here, there's almost no difference. And this is what the next slide says, right? So most of the delta G in the reactions is close to zero. It's like positive or -1. So these reactions are very close to equilibrium. So they can be very easily reversed if a slight change in in the concentration happens. But that's why the 3 steps with the strongly negative delta G is important for us, so the forward reactions can happen. So like I said again, these 3, because I can see that like the delta G here is massive compared to the others where barely any difference can be seen. So those are the 3 important reactions for glycolysis to happen, because in those reactions, if I actually want to reverse the reaction, if I want to make my backward reaction happen, I'm going to have to change the concentration by a lot, by 10 to the power of 3 or 6 times, which is a lot, and it's unreasonable. So I can easily say that my forward reaction is going to happen, and yeah, like glycolysis is going to proceed. And the reaction is heading towards equilibrium. I'm not really sure what you mean. Like the other reactions, since delta G is close to 0, yes, they're near equilibrium. But these 3 specific reactions, they're strongly exergonic, so they're going to go forward, not equilibrium. And we're done with the lecture. If you have any questions, you can ask. Yeah, go ahead. I'll see if I can answer. Honestly, I have nothing, because when I was in first year, we did not have mole SEQs. I think it's better to ask someone else. I personally only used the lectures during mole. Yep, I do feel bad for you guys. You have so much extra stuff. They might ask calculations, and they might ask basic concepts like, like, okay, delta H is negative. What does this mean? So you have to say is it exothermic or endothermic? Things like that. So have a basic understanding, and yes, there absolutely could be calculations. Welcome. If delta G is positive, what happens to energy? The reaction is going to need energy to go forward. You have to give it reaction. It's going to absorb. So like, for example, if it's a non-spontaneous reaction, it's going to absorb energy from the surroundings, or you need to heat it, for example, to get your reaction to begin. That's what delta G positive means. All right. I hope no more questions. Will they focus? I have no idea what lectures they're going to focus on. All right. I think, yeah, I think we're done. I hope no more questions. Or if you have any more questions, you can ask the GND people and they can get back to me. Well, bye, and thank you for listening.